Welcome to What is Software Engineering? After watching this video, you will be able to define software engineering, list the responsibilities of a software engineer, and compare and contrast software developers and software engineers. Software engineering is the application of scientific principles to the design and creation of software. The field uses a systematic approach to collect and analyze business requirements in order to design, build, and test software applications to satisfy those business requirements. When computing began in the late 1950s, software engineering was a relatively undefined discipline, but over time it transformed into a modernized engineering field. The software engineering field became a discipline in the 1960s and evolved as new technologies were developed and the approach to software development became more scientific. Trends in software engineering transformed from ad hoc programming towards more formal and standardized methods. Initially, the creation of software lacked a formal development process. As the world widely adopted computers, software became increasingly integral to more aspects of life. The inefficiencies in the software development process made it difficult to meet the rapidly increasing demand for computing resources and complex software. This led to what is known as the software crisis, which began in the mid-1960s and lasted until the mid-1980s. During this period, software development often ran over budget, behind schedule, and consisted of unmanageable, buggy code. By the time older software solutions came to fruition, newer, better, and faster technologies had already been developed, causing software engineers to have to refactor their code or completely redesign their system. Often software development solutions that worked for small software systems did not scale to large complex projects. Now, some of these issues still exist today, although to a much lesser extent, due to the consistent application of engineering principles to the software development process. Computing resources have become more widely available, and standardized methodologies for software development allow for large complex solutions that scale. The solution to the software crisis involved transforming unorganized coding efforts into an established engineering discipline. The mid-1980s also saw a rise in the growth of computer-aided software engineering, or CASE, which also helped to relieve the software crisis. CASE tools can be divided into 6 categories: business analysis and modeling, development tools such as debugging environments, verification and validation tools, configuration management, metrics and measurement, and project management. Now, the term software engineer is often used interchangeably with software developer, but there are subtle differences. Software engineers are also developers, but the term software developer is usually deemed narrower in scope than that of a software engineer. A software engineer's knowledge is usually broader. Software engineers take a systematic big picture approach in their thinking to software development, whereas developers may have more creative approaches. And both software engineers and software developers have specialized knowledge, but software engineers use that knowledge to build entire systems, whereas software developers use their knowledge to write code to implement specific functionality within a system. Software engineers are often employed on larger scale projects, and they are focused on the broad structure rather than solving an immediate problem. Software engineers are tasked with designing, building, and maintaining software systems. Their responsibilities include writing and testing code and consulting with stakeholders such as clients, third-party software vendors, security specialists, and other team members. The adoption of a measured scientific approach to software development has influenced the way software is created and designed. Today, the development process is typically guided by the Software Development Lifecycle, or SDLC. The SDLC identifies the steps needed to develop high-quality software. Later in this module, we will discuss the SDLC, the traits of high-quality software, and roles common in the field of software engineering. In this video, you learned that software engineering is the systematic approach to design and development of software. Responsibilities of a software engineer include designing, building, and maintaining software systems, writing and testing code, and consulting with stakeholders, third-party vendors, security specialists, and other team members. And finally, software engineers build systems while software developers implement specific functionalities. In this video, we will hear from experts discussing software engineering.
I think software engineering is the process of using programming languages and engineering principles to build products. These products could look like web apps, mobile apps, desktop apps, operating systems, or even networking systems. It is a skill that's integral to the success of our modern society because without technology, we couldn't get a lot of things done today. Within software engineering, it's a very broad term. And so within software engineering, you have roles such as front-end, back-end, security, mobile, test, full stack, DevOps, cloud, data, and machine learning. And these are all different types of engineers within software engineering.
I would define software engineering as building and improving software from anywhere from design and architecture to the user interface to fixing small bugs. So anything that falls in that range, that's what software engineers do.
So software engineering to me, I think really has to do with I consider it a creative process, and it fundamentally is the practice of designing, envisioning, implementing, and then supporting and maintaining software through the full life cycle of it. So not just writing code, but in thinking about the software you're building before you've even written a line of code, the journey from idea inception to actual implementation and launching of said software, and then maintaining it, improving it, supporting it, and potentially evolving it to something else. So it's very much a sort of creative and full life cycle end-to-end engineering process.
I know in the United States, at least, software engineering, software development, programming, they all have, depending on who you ask, they mean very specific things or very hazy things or very contradictory things, or it's like, why do we even have 3 different titles for the same thing? I think of those titles as kind of all meaning the same thing.
What's the difference between a software engineer and a developer?
I think the difference for me, I consider engineering to be a little bit sort of broader, software engineering to be broader than development. I think development to me means is sort of one part of the process. So I think one fundamental difference for me is I think software engineering is beyond just writing code, which I think a developer often is handed a task to write a piece of code or create a module, piece of software, whatever term you want to use. And I think engineering involves sort of starting a very long time before you even get to the development process and continues on beyond the time you would actually take your code, deploy it. So this kind of goes into the full life cycle.
In my opinion, there isn't a difference really. So for example, I was trained as a full stack engineer or a full stack developer, but I was hired as a software engineer to work on the front end of the company's application. So I think it's a matter of semantics, and a lot of it I think is a lot of gatekeeping to keep people who don't know anything about the industry out. Somebody who has studied CS may argue differently from I do, but as a person with a non-traditional path into the world of software engineering, I only see it as like title changes and title differences, and I think it depends on what company you work in and what company you work for, because at the end of the day, we're all using the same tools and technology to get the product shipped to production.
I think that they are pretty similar roles. They are used interchangeably a lot, I think. But I think the main difference is that software engineers are also responsible for the system design and architecture, as well as data, how it's received, used, and how it's disseminated, whereas software developers, I think, focus more on the building of apps and features.
So in Canada, being a computer programmer or a software developer is incredibly different than being a computer engineer or a software engineer, where to be an engineer, it means you've taken specific classes in like codes of ethics. and you're held to the same ethical standards as a civil engineer or a mechanical engineer. And so depending on where you are, the titles can mean very different things. And I know for like purposes of immigration, the titles also can mean very specific things, and you have to be careful about like what it is that you put down. But in job descriptions, I kind of see them all used interchangeably, and I tend to just kind of think of them all as the same thing.
It's much of more of a longer time horizon, I think, in terms of engineering versus development. And I think there's a lot more considerations and hats you need to put on throughout the software engineering life cycle versus the kind of more narrowly scoped development cycle.
Welcome to the introduction to the software development lifecycle. After watching this video, you will be able to describe what the software development lifecycle is, explain its history, and discuss some key advantages of using it. The software development lifecycle, known as the SDLC, is a systematic process to develop high-quality software in a predictable timeframe and budget. The goal of the SDLC is to produce software that meets a client's business requirements. The SDLC defines phases of the software development process that encompass their own process and deliverables. It's a cycle of planning, design, and development that can be implemented as an iterative approach to software development. Adherence to the SDLC minimizes risks and costs to the development of high-quality, deployable software. The software development lifecycle began to take shape in the mid-1960s as software development began to necessitate a more detailed approach because of its growing complexity. The SDLC led to a more deliberate approach as large corporations needed to manage complex business systems requiring heavy computational resources. In its initial conception, it used what is called the waterfall method to manage projects where the development of software follows a linear pattern through discrete stages. The SDLC has since been adapted, however, to more iterative methods in response to addressing customer needs and shifting requirements. Waterfall and other approaches to software development will be discussed in another lesson. There are some key advantages for businesses in following the SDLC. The first advantage is that it gives development teams a process to follow rather than using an ad hoc approach to improve efficiency and reduce risks. Secondly, there are discrete phases to the SDLC. Each phase is well defined so that team members know what they should be working on and when. The phases of the SDLC will be discussed in another video. Because of the well-defined phases, it facilitates communication between the customer, other stakeholders, and the development team. The SDLC offers an overview of the process so stakeholders know where they fit into that process. Also, since each phase is discrete, cross-domain teams know when they have completed their tasks and when development can move to the next phase. The SDLC provides room for iteration, where at the end of a cycle, the process can circle back to incorporate additional requirements as needed. Problem solving is incorporated early in the cycle, so problems are addressed in a timely fashion and can be addressed in the design phase rather than during coding. Finally, each team member has a well-defined role which reduces conflict and overlapping responsibilities. In this video, you learned that the SDLC provides a systematic process for software development. Its initial development in the 60s and 70s was driven by the need for a systematic approach because of the growing complexity of software. And key advantages of the SDLC include a roadmap to the software development process helping to reduce risk and improve efficiency, increased communication between the team and stakeholders, clearly defined and understood responsibilities for each team member, and the ability to be used iteratively, allowing for changing requirements. Welcome to the phases of the software development lifecycle. After watching this video, you will be able to name the phases involved in the SDLC, describe each phase, and identify several tasks associated with each phase. There are generally 6 phases in the SDLC process: planning, design, development, testing, deployment, and maintenance. Each phase is discrete, meaning that tasks from a previous phase do not overlap with tasks in the next phase. The original SDLC was conceived as a traditional waterfall method, where the phases are linear, but have since been adapted to introduce iteration so that shifting requirements can be accommodated. Waterfall and other approaches to software development will be discussed in another video. Note that some organizations may have different names for each stage. For example, planning may be called requirements or strategy or analysis. Also, some organizations may have additional or fewer stages. In the first stage of the SDLC, the planning phase, requirements are gathered, analyzed, documented, and prioritized. When planning a software solution, the following factors must be considered: users of the solution, the overall purpose of the solution, data inputs and outputs, legal and regulatory compliance, risk identification, quality assurance requirements, allocation of human and financial resources, and project scheduling. As part of the planning process, labor and material costs are estimated and weighed against time constraints. Also, project teams are identified and roles of each team member are proposed. If stakeholders are struggling to define requirements, often the development team may produce prototypes during the planning stage to tease out those requirements. A prototype is a small-scale replica of the end product used to get stakeholder feedback and establish requirements. A prototype is used to test basic design ideas. Though prototyping usually occurs during the planning stage, prototyping can occur at various phases of the SDLC whenever requirements need to be reconsidered or clarified as the project develops. After requirements have been gathered, they are combined into a document called a Software Requirements Specification, or SRS document. The SRS needs to be clearly understood and approved by all stakeholders. The developers are also involved at this stage so they can gain a clear understanding of these requirements. Requirements and the SRS will be discussed in more detail in a later video. In the design phase, the requirements gathered from the SRS are used to develop the software architecture. Several team members work together at this stage to design the architecture. The architecture is reviewed by the stakeholders and team, and during this phase, prototypes can be designed. A prototype is a preliminary mock-up of the system or parts of the system used for demonstration purposes. The document created in this phase is called a design document and is used by developers during the next phase, which is the development phase. The development phase, sometimes called the building phase or the implementation phase, is when the developers start the coding process once the design document is completed. The project planners use the design document to determine and assign coding tasks. This phase often requires the use of programming tools, different programming languages, and software stacks. Organizations may also have standards or guidelines that need to be followed. The testing phase is next in the process once the coding is complete, and some large projects have dedicated testing teams. Code needs to be thoroughly tested to ensure it is stable, secure, and meets the requirements outlined in the SRS. Testing can be manual, automated, or a hybrid of both. Product bugs are reported, tracked, and fixed, and the code is retested until the software is stable. Some common levels of testing include unit testing, integration testing, system testing, and acceptance testing. Each of these testing levels will be described in further detail in another video. Next, the deployment phase is where the application is released into the production environment and made available to users. This can also happen in stages. First, it is released onto a user acceptance testing, also called UAT, platform, and once the customer signs off on the functionality, it is released to production. This approach can be used for making software available on a website, mobile device app store, or a software distribution server on a corporate network. Finally, the maintenance phase happens once the code has been deployed into a production environment. This phase helps to find any other bugs, identify user interface issues, or UI for short, and identify other requirements that may not have been listed in the SRS. Code enhancements can also be identified at this stage. If bugs are discovered in this phase that were missed during testing, these errors may need to be fixed for high-priority issues or incorporated into the requirements as part of a future software release, and the process can start over again. In this video, you learned that the SDLC can be divided into 6 phases. Planning involves requirement gathering and development of the SRS. The architecture is developed during the design phase and the design document is created. The development phase is when coding takes place, and then during the testing phase, issues with the code are found and fixed if possible. Deployment is when the code is released to the production environment. And finally, in the maintenance stage, feedback is collected from stakeholders, other UI issues may be identified, and code enhancements suggested. And this information can be fed into another software development cycle if necessary. Welcome to Building Quality Software. After watching this video, you will be able to list common software engineering processes and describe the common software engineering processes required for building high-quality software. There are numerous processes that are common to software engineering projects. In this video, we will discuss 6 of them: requirements gathering, design, coding for quality, testing, releases, and documenting. The Software Requirements Specification, or SRS, encompasses the process of collecting and documenting the set of requirements that the software needs to adhere to. It may include a set of use cases that describe the business needs and user flows that the software must implement. Software requirements can be classified into 4 broad categories: functional, external and user interface, or UI, system features, and non-functional. These categories are discussed in more detail in another video. Software design is the process of transforming the requirements into a structure that is implementable using code. The software design process translates the requirements into a language the developers can use to write the code. It transforms the requirements into a software solution. The technical lead breaks down requirements into sets of related components with clearly defined behaviors, boundaries, and interactions. These components define the system architecture. The system design incorporates guidance on system functions, performance, security, and platform characteristics. The design communicates business rules and application logic. Application programming interface design, which is how apps talk to each other or communicate with the database, user interfaces, and database design. Code quality refers to the characteristics of the code, including attributes such as maintainability, readability, testability, and security. Quality code must fulfill the intended requirements of the software without defects. Additionally, it should be clean and consistent, easy to read and maintain, well documented, and efficient. Coding for quality entails following a set of coding practices during development. These include following common coding standards, conventions, patterns, and styles, using automated tools known as linters to detect pragmatic and stylistic errors, and commenting in the code itself to make it easy for others to understand and modify. Software testing is the process of verifying that the software matches established requirements and is free of bugs. Its purpose is to identify errors, gaps, or missing requirements when compared with stated requirements. Properly tested software ensures reliability, security, performance, and efficiency. Software testing can often be automated or done manually. Levels of testing include unit, integration, system, and user acceptance. Unit testing is often done by the developer and tests the smallest component of code that can be isolated from the rest of the system. Once components are integrated into the larger product, integration testing occurs. Then, after the larger product is deemed completed, system testing can take place. User acceptance testing, or UAT for short, and sometimes called beta testing, is when the software is tested by the intended end user. Types of testing can broadly be divided into 3 categories: functional, non-functional, and regression. Testing levels and types will be further explained in an upcoming video. When the newest version of the software is distributed, it is referred to as a release. Different types of releases are intended for different audiences. There is generally an alpha, a beta, and a GA release. GA stands for General Availability. The alpha release is the first functioning version of the system released to a select group of stakeholders. The alpha release likely contains errors and may not contain the full feature set, but does contain most of the desired functionality. Design changes may still occur during this release stage. The beta release, also called a limited release, is given to the stakeholders outside of the developing organization. One of the intents of the beta release is to try out the software under real conditions, test the functionality, and identify any outstanding bugs or errors. The beta release should meet all the functional requirements. Then, after beta release, changes are agreed upon, made, and tested, and a stable version is released. The audience for the GA release is all users. Software documentation should be provided to both non-technical end users and technical users. System documentation is geared toward the technical user. Technical users may be other engineers, developers, or architects. System documentation explains how the software operates or how to use it. It consists of README files, inline comments, architecture and design documents, verification information, and maintenance guides. User documentation is provided to the non-technical end users to assist them in the use of the product. Generally, user documentation is provided in the form of user guides, instructional videos and manuals, online help, and inline help. More details about documentation will be discussed in another video. In this video, you learned that requirement gathering is collecting and documenting the set of requirements that the software needs to adhere to. Designing transforms requirements into a structure that developers can use. Coding for quality entails following a set of coding practices during development. Testing is the process of verifying that the software matches established requirements and is free of bugs. There are 3 types of releases, including alpha, beta, and general availability. And finally, documenting requires text or video that explains the software to technical and non-technical users. Welcome to Requirements. After watching this video, you will be able to describe the steps of the requirement gathering process, explain the purpose of a user requirement specification or URS document, explain the purpose of a software requirement specification or SRS document, and explain the purpose of a system requirement specification or SysRS document. Requirement gathering is a 6-step process of defining a problem to be solved and documenting how to go about solving that problem. These steps include identifying stakeholders, establishing goals and objectives, eliciting requirements from the stakeholders, documenting the requirements, analyzing and confirming the requirements, and prioritizing. Generally, the stakeholders work for the organization that requests the development of the software product. Key personnel from the organization may include decision makers, end users, system administrators, engineering, marketing, sales, and customer support personnel. It is good to have a representative from every group that the product affects. The goals of the product should be clearly defined. Goals are broad, long-term achievable outcomes. Goals can include customer outcomes and business goals. Next, objectives should be identified. Objectives are more specific than goals, and they are actionable and measurable actions that achieve the stated goals. The next 3 steps, eliciting, documenting, and requirement confirmation, are usually completed iteratively. Elicitation can be accomplished through surveys, questionnaires, and interviews. As the requirements emerge, they should be documented and checked to ensure they align with the goals and objectives. Documented requirements should be easily understood by stakeholders and the project team. In order to confirm the requirements, they should be analyzed to ensure consistency, clarity, and completeness. And after analysis, the requirements should be shared with and approved by the stakeholders. After confirmation, requirements should be prioritized. Labels such as must-have, highly desired, and nice-to-have are helpful. If possible, order the requirements within those categories. Typically, there may be 3 documents that result from the requirements gathering process: Software Requirement Specification, or SRS, User Requirement Specification, or URS, and System Requirement Specification, or SysRS. The most common of these is the Software Requirement Specification. The Software Requirement Specification, or SRS, is a document that captures the functionalities that the software should perform and also establishes benchmarks or service levels for its performance. Parts of an SRS include a purpose statement that contains the intended use of the SRS, its audience and scope, constraints, assumptions, and dependencies, and requirements which can be sorted into 4 categories: functional requirements, external interface requirements, system features, and non-functional requirements. The product's purpose describes who will have access to the SRS and how they should use it. The scope describes the benefits of the software, its goals, and objectives. And the second part of the SRS should detail constraints, assumptions, and dependencies. Constraints describe how the product must operate under given conditions that may limit options in the design phase, such as conformation to standards or hardware limitations. Assumptions may include things like a required operating system or hardware that is needed by the software to function. Dependencies on other software products should also be noted. Requirements can be classified into 4 categories. Functional requirements are those that cover the functionalities of the software. External requirements are the requirements that address the behavior of the software in relation to external entities, such as users and interactions with other hardware or software. System features are a subset of functional requirements. These are required features for the system to function. There are also non-functional requirements, such as specifying performance, safety, security, and quality standards. User requirements describe the business need and expectations of the end users from the software system. The user requirements are written as user stories or use cases that answer 3 questions. Who is the user? What is the function that needs to be performed? And why does the user want this functionality? User acceptance testing determines if these requirements have been met. Often, though, the user requirements and software requirements are combined into a single SRS document. The SRS details the expectations of the software system. The System Requirement Specification document, or SysRS, to differentiate it from the SRS, clearly outlines the requirements of an entire system. The System Requirement Specification is often used interchangeably with Software Requirement Specification, but the SysRS is actually broader in scope than the SRS. Many software projects develop an SRS rather than a SysRS. The SysRS contains system capabilities, interfaces, and user characteristics. It also may include policy requirements, regulation requirements, personnel requirements, performance requirements, security requirements, and system acceptance criteria. It also outlines expectations of the hardware needed for the system in addition to software requirements. In this video, you learned that the requirement gathering process entails identifying stakeholders, establishing goals and objectives, and eliciting, documenting, confirming, and then prioritizing requirements. The SRS documents functional, external, system, and non-functional requirements. The URS documents user stories. And finally, the SysRS documents system capabilities and acceptance criteria, and policy, regulation, personnel, performance, security, and hardware requirements. Welcome to Software Development Methodologies. After watching this video, you will be able to list several commonly used approaches to the software development lifecycle, explain waterfall, V-shape model, and agile methods, and compare the pros and cons of each of these 3 methods. There are many ways to approach software development. A specific methodology for developing software is commonly used in order to assist the development team to clarify communication among team members and determine how and when the information is shared. In this video, we will discuss 3 of these approaches: waterfall, V-shaped model, and agile. In the beginning, when the SDLC was conceived, it implemented what is known as the waterfall method. Waterfall is a sequential method of software development where the output of one phase is the input for the next phase of the cycle. Development and work on the next phase start only after the completion of the previous phase. All planning, such as defining requirements and architectural design, is done up front. The customer usually does not see the product until it is in the testing phase. For a major version release of the product, the same process is repeated, resulting in long intervals, such as years, between releases. The V-shaped model is named as such because the phases form the shape of a V. The phases going down the left side of the V are called verification. Then, going up the right side of the V, those phases are called validation. The V-shaped model is like waterfall in that it is also sequential. Each phase in verification corresponds with a validation phase. There are 4 stages that occur on each side of the V. Going down the V are planning, system design, architecture design, and then module design. The bottom of the V is the coding phase. And going back up the V are the 4 phases that correspond to the phases going down the V: unit testing, integration testing, system testing, and acceptance testing. The tests are written during the verification phases on the left and executed during the validation stages on the right. Now, the Agile model is different. It focuses on a collaborative software development process over multiple short cycles rather than a strictly top-down linear process. Agile is what is called an iterative approach to development. It still aligns with the SDLC, but each phase is short. Teams work in cycles, or sprints, which are usually 1 to 4 weeks long. Unit testing happens in each sprint to minimize the risk of failure. Rather than the maintenance stage of the SDLC, the final stage of the sprint is a feedback stage. At the end of each sprint, a chunk of working code is released at a meeting called the sprint demo, where stakeholders can see the new functionality and provide feedback. After the sprint demo, the entire process is repeated for every sprint cycle. After several sprint cycles, a minimum viable product, or MVP, is developed so stakeholders can provide feedback on the basic feature set. The MVP contains a feature set to validate assumptions about the software. The 4 core values of Agile development outlined in what is known as the Agile Manifesto are individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, and responding to change over following a plan. The main difference between traditional SDLC methods, such as waterfall and the V-shaped model, compared to the Agile method of software development, is the former are sequential, whereas Agile is cyclical. Traditional SDLC methods, such as waterfall and V-shape, center around the whole product being developed before soliciting customer feedback, whereas Agile focuses on quick, short bursts of development. There are pros and cons to each method, though Agile is probably the most popular method used in modern software development. Regarding the pros of the waterfall method, it is easy to understand and follow. Each stage is discrete and well-defined, making it easy for all team members to understand their roles. Also, since planning is done up front, it is easier than iterative methods to estimate a budget and allocate resources. That said, waterfall lacks flexibility. Since all planning is done up front, if a requirement is changed or overlooked, that change can be hard to incorporate at a later date. Inevitably, unforeseen complications happen or agreed-upon functionality shifts from what was initially envisioned. Like waterfall, the V-shaped model is simple and easy to use. It is even more rigid than waterfall, but designing test plans during the verification phase saves considerable time during coding and validation phases. Drawbacks are also similar to waterfall because it does not readily accommodate changing requirements. Once an application is in the testing phase, it is extremely difficult to go back and change functionality. Agile development is different, relying on ongoing research, planning, and testing during product development. When adding new features to a product, development still goes through the same phases as in traditional SDLC. But with Agile, new and changing requirements are handled quickly and easily because planning is initiated at the beginning of each sprint cycle. Most resources are spent on the building phase. At the end of each cycle, the QA team, stakeholders, and the customer have some piece of working code to test against requirements and are encouraged to provide feedback. As coding languages and technologies have developed in recent years, they now allow for modular design where developers can focus on smaller chunks of code that are readily integrated into the larger product. These small chunks can be released to provide the MVP. Cons of Agile are that upfront planning, such as budgeting and scheduling, can be challenging because the overall scope of the product is not clearly defined. In this video, you learned that 3 of the common approaches to software development include waterfall, V-shape model, and Agile. Waterfall and V-shape are sequential, whereas Agile is iterative. Both waterfall and V-shape models are easy to implement, but neither accommodates changing requirements well. And Agile allows for changing requirements, but resource allocation can be challenging. Welcome to Software Versions. After watching this video, you will be able to discuss software versions on computing platforms and identify software versions and numbering. Software versions tell us a lot about programs and applications. Users can determine what software version they are using, and developers can provide useful information with version numbers. Software version numbers vary in length and meaning. However, most version numbers follow a similar format and represent similar information. Version numbers indicate when the software was released, when it was updated, and if any minor changes or patches were made to the software. Software versioning is how software developers keep track of new software, updates, and patches for programs and applications. Version numbers can be displayed in several ways. Version numbers can be short or long depending on the software and the preference of the developer with 2, 3, or 4 number sets. Each number set is divided by a period. The first release of an application or program might have a 1.0 as the version number to indicate no updates, patches, or fixes to the software. Note, a version still in beta or testing could have a version number lower than 1, such as 0.9. A program or application with many releases and updates will have a longer number, sometimes 4 different number sets within the version number. Some software developers may use dates for their versioning. For example, Ubuntu Linux version 18.04.2 was released in 2018 April. The third number set, .2, designates an additional change or update. What do these numbers mean? Some version numbers follow the semantic numbering system and have 4 parts separated by a period, but not all numbering systems follow this 4-part example. In semantic numbering, the first number indicates major changes to the software, such as a new release. The second number indicates that minor changes were made to the software. The third number in the version number indicates patches or minor bug fixes. And finally, the fourth number indicates a build number or build date, and it can indicate less significant changes made. Software version numbers are identified in the About or Help section of software. You can practice identifying your version number in a web browser. This example illustrates how to view the version number in the Google Chrome desktop web browser. However, if you are using a different web browser, you should be able to follow the same or similar steps. To view the web browser version, first select the 3 dots or 3 lines in the top right corner of your browser. Next, select the menu item, Help, then select About to view the version information. The version of your web browser will display. Are newer versions of software compatible with older versions? Lack of compatibility between old and new versions of software is a common problem. You can troubleshoot compatibility issues by viewing the software version to determine if you are using an outdated version of the software. Sometimes updating software to a newer version will resolve compatibility issues. Some software is backwards compatible. If a program or application is backwards compatible, then the older versions of files, programs, and systems will work properly with newer versions. In this video, you learned that version numbers indicate the history of changes, updates, and patches to software. Some version numbers follow the semantic numbering system and have 4 parts separated by a period. Compatibility with old and new versions of software is a common problem, and you should view the version of the software you are using to determine software compatibility. Welcome to software testing. After watching this video, you will be able to define the terms functional testing, non-functional testing, and regression testing, and compare and contrast typical testing levels. Software testing is the practice of integrating quality checks throughout the software development cycle. The purpose of testing is to check whether the software matches expected requirements and ensure error-free software. In order to test software, the team writes test cases. These test cases are written to verify the functionality of a software application and ensure requirements have been satisfied. Test cases can be written in different stages of the SDLC and may vary depending on the type of test or the method used to develop the software, such as agile or waterfall. A test case contains steps, inputs, data, and the expected corresponding outputs. Regardless of the test type or development method, test cases should always be written after requirements are finalized. Software testing helps evaluate the software to identify whether or not the software product meets requirements and is error-free. Types of testing can be broadly classified into 3 categories: functional testing, non-functional testing, and regression testing. Functional testing usually involves black box testing, which is a method of testing without looking at source code or internal structure. Functional testing is only concerned with inputs and corresponding outputs of the system under test, also called the SUT. It is entirely based on testing functional requirements, and functional testing can be carried out manually or using automated tools. The goal is to test the functionality of the application, making sure the application is usable and accessible. Functional testing tests the SUT to make sure it meets functional requirements. Functional testing makes sure that when user errors or input edge cases do occur, the software handles those exceptions seamlessly by displaying appropriate error messages. Non-functional testing includes testing the application for attributes like performance, security, scalability, and availability. Non-functional testing checks to see if the SUT's non-functional behavior is performing properly. Non-functional testing should answer questions like the following: how does the application behave under stress? What happens when many users log in at the same time? Are the instructions in documents and user manuals consistent with the application's behavior? Does the application behave similarly under different operating systems? How does the application handle disaster recovery? And how secure is the application? Regression testing, also called maintenance testing, confirms that a recent change to the application, such as a bug fix, does not adversely affect already existing functionality. Regression testing should occur when there has been a change in requirements or when defects have been fixed. In order to conduct regression testing, all or some of the test cases should be selected to test against the application. Regression test case selection and prioritization can be challenging and can depend on several factors. Common reasons for regression test case selection include cases that have frequent defects, contain frequently used functionality, contain features with recent changes, or are complex test cases, edge cases, and randomly successful or failed test cases. Now that we have discussed different types of testing, let's discuss testing levels. There are 4 testing levels: unit, integration, system, and acceptance. Each level occurs at a different time in the SDLC. There are 4 different levels in order to reduce the amount of time spent on testing by preventing overlap. We will discuss each of these testing levels next. Unit testing refers to the tests that verify the functionality of a specific section of code, usually at the function level. It is performed by the software developer or engineer during the development phase of the software development lifecycle. Unit testing aims to eliminate construction errors before code is integrated with other modules. Unit testing is intended to increase the quality of the resulting software, as well as the efficiency of the overall development process. Integration testing seeks to identify errors when 2 or more smaller independent code modules are combined. Integration testing is another type of black box testing. Prior to integration testing, smaller independent code modules that passed unit testing are incorporated into the larger software application. After modules are integrated together, then integration testing can occur. Integration testing exposes bugs that occur when those smaller units of code interact with each other. Integration testing uncovers deficiencies in communication with a new module in conjunction with other existing modules, databases, or external hardware. Integration testing uncovers situations where bugs develop due to differing programming logic between modules, for instance. Also, sometimes during module development, requirements change, and the module isn't fully unit tested. Poor exception handling can cause problems when modules are integrated together. System testing occurs after integration testing and is conducted on a complete integrated system to evaluate the system's compliance with its specified requirements. It validates the system as a fully completed software product. System testing is both functional and non-functional. And system testing is done in a staging environment, which should be similar to the production environment. And finally, acceptance testing is formal testing with respect to user needs, requirements, and business processes. It determines whether a system satisfies the needs of the users, customers, and other stakeholders. Acceptance testing is usually done by the customer or the stakeholders during the maintenance stage of the SDLC. In this video, you learned that there are 3 categories of testing: functional, non-functional, and regression. Unit testing verifies small independent chunks of code. Integration testing looks for errors when 2 or more small chunks of code are combined. System testing validates the system as a fully completed software product. And acceptance testing verifies correct implementation of user requirements and business processes. Hello and welcome to Software Documentation. After watching this video, you will be able to list documentation formats, compare and contrast product documentation to process documentation, describe the categories and types of documentation, and explain the purpose of standard operating procedures. Software documentation is information about the software that describes what the product is and how to use it. These can be written, video, or graphical assets associated with a software product's development and use. Documentation can be in any of these 3 formats. Documentation is an essential aspect of software engineering applicable across all the phases of SDLC. Software documentation can be written for different types of audiences, such as end users, software developers, QA engineers, system administrators, and other stakeholders. Documentation can be divided into 2 categories: product and process. Product documentation relates to the product's functionality, whereas process documentation describes how to complete a task. Process documentation should provide the requirements for the quality implementation of a business process. Okay, now let's discuss some specific types of product documentation. There are many types of documentation, and we will discuss 5 categories, including requirements, design, technical, quality assurance, and user documentation. Requirements documentation is written during the planning phase of the SDLC and is intended for the development team, including the developers, architects, and QA personnel. Requirements documentation describes the expected features and functionality of the software system. It includes the software requirements specifications, system requirement specifications, and user acceptance specifications. Design documentation is written by the software architects and the development team to explain how the software will be built to meet the requirements. It consists of both conceptual and technical design documents. Technical documentation includes comments written in the code to help other developers read the code to understand its behavior. It also may include working papers that explain how the code works and documents that record engineers' ideas and thoughts during project implementation. Quality assurance documentation includes all documents that pertain to a testing team's strategy, progress, and metrics. Types of test documentation include test plans, test data, test scenarios, test cases, test strategies, and traceability matrices. Traceability matrices map test cases to their requirements. User documentation is intended for end users and explains how to operate the software or help them to install or troubleshoot the system. End user documentation includes frequently asked questions, installation and help guides, tutorials, and user manuals. Standard operating procedures, called SOPs, often accompany process documentation. Process documentation provides an overview of a process, but SOPs go through much greater detail. The SOP is written documentation that explains step by step how to accomplish a common yet complex task that is organization specific. For example, checking in code using a code repository is common knowledge for a software engineer. However, an organization might have specific steps to follow for that organization in order to get code merged into the main branch. The SOP documentation explains those steps in detail. SOPs can be in the form of a flowchart, a hierarchical outline, or step-by-step instructions. Documentation in any form must be kept up to date. Take, for instance, online user manuals. If a cloud-based application user interface changes, then the accompanying online documentation must be updated accordingly. Businesses need to ensure they allot resources for this step. With regards to the software development in the SDLC, updating documentation happens during the maintenance phase. Ideally, documentation should also be reviewed periodically to ensure its accuracy. In this video, you learned that documentation comes in 3 formats: written, video, or graphical. Process documentation describes how to complete a task. Product documentation relates to how a product functions. The types of product documentation include requirements, design, technical, QA, and user. And SOPs are written instructions detailing an organization-specific procedure. Welcome to Roles in Software Engineering Projects. After watching this video, you will be able to list the common roles on a software engineering project, describe each role, and explain the responsibilities of each role. There are several common roles on a software development project, and these roles can have different names depending on the approach being used, such as Agile or Waterfall. Sometimes different companies have different names for similar jobs, but not all projects will have all these roles. The roles we will discuss in this video are Project Manager or Scrum Master, Stakeholder, System or Software Architect, UX Designer, Software Developer, Tester or QA Engineer, Site Reliability or Ops Engineer, Product Manager or Owner, and Technical Writer or Information Developer. Now let's describe each role and some of the responsibilities for each job. Traditional SDLC methods have project managers, but in Agile, the equivalent role is called a Scrum Master. A project manager makes sure the project runs smoothly and facilitates communication about the project. The project manager often deals with bigger picture issues such as planning, scheduling, and budgeting, allocating personnel and resources, executing the software plan, and team communication. In Agile, there is a Scrum Master. Rather than focusing on planning, the Scrum Master is focused on ensuring team and individual success. Remember that the 4 core Agile values prioritize people and communication over processes, and the Scrum Master is responsible for facilitating that communication. The stakeholders are the people for whom the product is being designed. They include individuals such as the customer, end users, decision makers, system administrators, and other key personnel. The stakeholder is mainly responsible for defining project requirements and providing feedback if the team members need clarification on requirements or if a proposed solution cannot be solved as planned. The stakeholders may also sometimes participate in beta testing and acceptance testing before the software is released. The system architect designs and describes the architecture of a project as well as communicates that architecture to team members. They are sometimes also called a software architect or a solution architect. They are responsible for designing the essential characteristics of the inner structure and technical aspects of the software. The architect provides technical support across the different stages of the SDLC. Note, software architecture will be discussed in further detail in another module. UX means user experience. The goal of a UX designer is to balance making the software intuitive, but also as robust as it needs to be to address requirements. They define how the software behaves from the user's perspective. The UX designer determines how the software communicates its functionality to the end user and how the end user interacts with it. Next, the developers write the code that powers the software. Responsibilities include implementing the architecture laid out in the design document, incorporating the requirements laid out in the software requirements specification, and employing the UX requirements determined by the UX designers. Testers, or QA engineers, are in charge of ensuring the quality of the product and that the software solution meets customer requirements. They are responsible for writing and executing test cases to identify bugs or deficiencies and provide this feedback to the development teams. A site reliability engineer, sometimes called an SRE or ops engineer, bridges development and operations by combining software engineering expertise with IT systems management. They track incidents and facilitate meetings to discuss them. They also automate systems, procedures, and processes, assist with troubleshooting, and ensure reliability for the customer. The product manager or product owner has the vision of what the product should look like. They have an intimate understanding of the client's requirements and the end user's needs. They are responsible for leading development efforts to create the software and for ensuring the product provides the value stakeholders are looking for. Finally, the technical writer or information developer writes documentation for the end user. They write documentation on technical material geared towards a non-technical audience. Not only does this documentation help the end user to use the software, but it also helps the customer so they can provide timely feedback to the development teams. Technical writers may be asked to write user manuals, reports, white papers, and press releases. In this video, you learned that there are a variety of job roles on a software development project, and each occupation has responsibilities unique to each role. Welcome to Insider's Viewpoints, Job Roles in Software Engineering Teams. In this video, we will hear from experts discussing the various job roles you can expect to work with on your software engineering team.
Yeah, so on the engineering team I worked with, we had a product manager, we had a tech lead, we had a few QA analysts or test engineers, and we also had access to UX designers. And so the product manager ensured that we were on task and on track to deliver the features that we said we were going to build according to the business needs. That way we're not left behind.
Yeah, I think in my experience, the roles that software engineers would interact with the most, I think would, in no particular order, product managers. So the folks who are actually sort of working with the sales teams, the marketing teams, figuring out what actually needs to be built, what are customer needs, what are innovations and ideas that, looking forward that you might want to invest in and build out.
We asked our experts to describe these job roles in software engineering teams in further detail.
I think software engineering these days, as it becomes more and more, it's more and more large scale, more complex, more systems at play, more considerations. There's just a lot of things to consider in today's world as a software engineer. So you often work with a project or program manager who helps you set up your timelines, helps you ensure you're meeting your goals, helps you unblock yourself, helps you keep your stakeholders up to date with what is happening with your project. So there's just a lot of pieces involved, and I think project and program managers really are there to help tie it all together.
So the product manager would always act somewhat like a scrum master. So like we would have stand-ups and we would talk about the tickets that we had in Jira, and it was like, okay, so what are you working on? What do you need help with? And are there any issues? And during that process, the product manager does ensure that we were on task and on track, and if we had any issues, he would help us to resolve it.
You'll have a software engineer who's more focused on the architecture, and they can keep the big picture in their brain more easily. And then some software engineers who are more the nitty gritty. I'm sitting down and I am writing code, and my job is to like turn business logic into computer logic. And some companies have those all split out as different roles.
I think software engineers and these roles, the more they're embedded and work closely together and actually collaborate as part of a single team, versus handing off things in a more waterfall approach. I think that's generally the best way, or one of the most effective ways, is to actually work together as much as possible. Regular check-ins, actually having brainstorming sessions, group chats that involve all the various folks from all the roles. I think close collaboration there is super key.
And at some companies, all the different hats have their own titles. So you might be talking to a software engineer who's actually doing more kind of DevOps, infrastructure building, monitoring and alerting kinds of work. And then there's a software engineer who's also doing QA work, and they're the ones who are focusing on pipelines and continuous development, continuous integration type projects, working on getting test suites and automation all set up.
In terms of working with the UX designer or the UX engineer, they would give me like specific specs from Figma in order to meet the certain specifications of the business. And let's say we're building a checkout page, so the UX designer would design the spec out page in Figma and then deliver that spec to me, and then I would code it according to the design.
UX designers who actually come up with if you are working on and engineering a user interface, you'll work with UX designers to essentially from the moment of sketching out sort of a draft on paper or a whiteboard of an idea, all the way down to working with them on mocks and implementing the mocks and iterating on those. UX researchers often are worked with when you actually need to go out and do research in market and interview your partners or customers to get sort of as real time as possible and just real feedback from real users of your software.
So once I code something, I get it reviewed by my tech lead or my senior engineer. It would go to QA for them to test the application to ensure that whatever I did or implemented didn't break anything. If something is broken that I didn't catch, the QA tester would write up like a test plan or would do like a detailed testing document. That way I understood exactly what needed to be resolved, and I would resolve it and then go back to the QA person and say, hey, this is fixed, can you take a look at it again? And they would tell me whether or not it's fixed and whether or not something else was broken, which often happens with code.
So you generally work a lot with product managers because you need to know what to build. They generally give you a lot of guidance on on what they want to build, and you collaborate with them in terms of how to build it and discuss trade-offs and timelines and expectations. So it's a very much a collaborative process.
Typically, I have found that I interact most with product owners. So either at some places it's been a customer who works inside the company, and so I go to them quite frequently for questions on clarifying refinements, for getting test schedules up and running, for figuring out pain points and trying to optimize their workflows using technology to support them.
Software engineers work often with site reliability engineers, or sysadmins is maybe the role could be called, to actually maintain and help run the software and deploy it and actually get it running somewhere that's not on your desktop. You often work with more dedicated test engineers who are responsible for end-to-end testing, automated testing, integration testing at all points of the life cycle.
So as an engineer, you're never alone, you're never working alone. It's just a matter of knowing how to communicate directly with the people on your team.